So, remember last time we were discussing the effect of the fact that the electron in an atom is orbiting. We mentioned the fact that if you have an electron orbiting like that, it's essentially a little dipole, which creates a magnetic field. Well, actually, I did this right for the right-hand rule, but since it's a negative charge, isn't the magnetic field going to go the other way? Not that it matters much. The point is that it does that, and we don't want to be drawing magnetic fields. I simply want the fact that there's a magnetic dipole moment, which is that. I derived that last time in a slightly hand-wavy way, but it turns out you can make the argument as rigorous as you like, and that's still the same answer. Remember, a magnetic dipole is defined as the current times the area. Okay? So there's let me go ahead and erase these magnetic fields. You're supposed to remember that they're there. But what I really just want to have is that if I have this electron in this orbit, the angular momentum, I think of that way, and there's a dipole moment that's pointing in the same direction. Now, what's the effect of a dipole? I said, the reason we're talking about this is because, well, this is one of the basic things the electron's doing, and we know there's an electric interaction between the electron and the electric field, but there's also an interaction between the electron and a magnetic field. There's two sorts of things that happen when you have a dipole, magnetic dipole. One is there's a torque, which is mu cross B. I won't derive that. This is a result from electricity and magnetism that you get this torque. You can go back to your E&M book. Actually, I'm not sure. Did you guys learn that last semester? Yeah. Did you derive it or just learn it? Huh? Right. You'll get it next time. The derivation's a little bit subtle, but there it is. Okay, so let's remind ourselves what that does. If my picture is that the magnetic field is like that, and the magnetic moment is like that, mu cross B is a torque that's pointing that way. Now, of course, the notion of torque, right, it's a little bit funny. A torque is torque isn't necessarily a force. It's a force, but the direction of it's a little bit funny. The way this works out right is that if F equals ma, this is also equal to, well, that's m, sorry, that's ma, that's mv dot, which is p dot. I said that before. If I take r cross f, that's torque. And so that's r cross p dot. And that's equal to d by dt of r cross p. But I cheated. I put the derivative outside of r, so I better do that. But this term is v cross mv, so that's 0. This is angular momentum, r cross p. So torque, and I took the time derivative of it. Torque is dl dt. You should have known this. I'm just repeating something you learned but may have forgotten. Okay? So then what I have is that dl dt, which is the torque, so the torque changes the angular momentum. Torque is this funnily defined thing where I take mu cross b. It's not obvious what's the physical meaning of the torque, at least in terms of its direction. And the answer is, well, that's the direction the angular momentum is going to get a change in. is, sorry, dl dt is mu cross b. All right, and mu is minus e over 2m times L. All right. Now, I want to examine this, but let me just take a special case of, to make it simple, let me think of this being a right angle. You can generalize this to it not being a right angle. It's not very illuminating. So then the torque is in the plane, or suppose that, so this is, say, x, y. If I look at it from above, if this is x, y, this was mu, and that's b. This is mu, and L is in the same direction. So let me just draw L. I have L like this, okay? The torque is like that, which is dl dt. So you can see that I have the angular momentum vector like this in this plane, and then the change in angular momentum is completely perpendicular to that. Remember, a magnetic field doesn't change magnitudes. If you have just a particle moving and it has charge and there's a magnetic field, the force is always sideways and you don't actually change the velocity. This is a similar setup where if I have the angular momentum and then the torque is sideways to it, it's not going to change the magnitude of L. It's just going to make L rotate. Okay? In particular, let me redraw this. If here's L as a vector, just like I did with an R vector, L dot is the magnitude of L changing in the L hat direction, if you will, times L theta dot, where that's a theta, in the theta hat direction. That being theta hat, and that being L hat, okay? I've said that this magnitude's not going to change, because if I think about this a second, since it's perpendicular to L, it's not going to change the magnitude, okay? So finally, L theta dot is just minus E over 2m LB. L cancels out, and theta dot is indeed just, so this is theta dot, that's just omega, right? That's just the definition of omega. Omega, which we think of as 2 pi f, which we can also think of as 2 pi over the period, is just the time derivative of the angle. All of that was simply to get you that there's this relationship here. Okay? I don't want to emphasize this. I'm not going to examine you on this. I wanted to show you it's fairly straightforward, but this is a basic result about these systems. When you have an electron in an atom, and it's got some angular momentum, if you have a magnetic field, what it's going to do is the angular momentum vector is going to rotate. That's to say the magnetic moment's going to rotate. That's so that if I think of the magnetic field as being up, I could have thought of the original rotation of the electron in the atom being like that, so that the magnetic moment is out that way, and then that thing is going to rotate. So that's precession, right? It's like what the pole of the Earth does on the 26,000 year, 16,000 year time scale, right? Okay, so just simple precession. This is called the Larmor frequency. And it's important because you can readily measure it. If you apply a magnetic field to an electronic system and then probe the atom somehow, and I won't get into the details of how this is done, you can see that once the magnetic field is applied, they're sort of oscillating, precessing at this frequency, and as you change B, you can change omega. So this is a really extremely robust, well-measured, understood result in atomic physics, okay? And it's just worth knowing in general. And of course, Well, okay, let me leave it at that. So this is sort of just for your just general knowledge that this is what happens. Okay, so there's a second effect, though, that again maybe isn't intrinsically interesting, but it turns out we learned something very important from it. Or it's not intrinsically that interesting, although I think it's worth knowing. If you apply a magnetic field to a dipole, you can also get a force. And the way to think about this is that there is an energy, which is minus mu dot B. That's potential energy. So again, if I have B like that, and I have mu like that, mu dot B would be, let's say that this is in the Z direction. So B is purely in the Z direction. This would then just be minus mu sub Z times B. Now remember, mu is minus E over 2m. Well, let me take off the negative side and just say, sorry, instead of writing minus E over 2m for the electron, let me just write Q for a general charge, times L, the vector. But here I'm taking just the Z component of the vector, right? Because I have that. So let me just take the Z component, because I'm doing mu dot B and I've put B along Z. So this is minus Q m sub L h bar over 2m B. That's a potential. So I'll have this potential. Now, whenever I have a potential, the reason I talked about a potential is because there's a force. The force is the change in the derivative of the potential. In one dimension, it's the derivative of the potential. In multiple dimensions, in general, it's the gradient of the potential. So if B is constant, then all of these things are constant. If B is uniform, there's no force. Okay? But if the magnetic field is not constant, then the fact that the magnetic field isn't constant is going to make this, it's going to make the atom move. It's going to make the electron move. All right? Simple enough. And then that's a way to measure m sub L and sort of probe this quantum mechanical system. I mean, after all, it is a good question. We worked out all these rules about an atom, and the Bohr atom, and of course, you do directly get to measure, I mean, the first result was beautiful. It explained the light that's seen from atoms, the energy levels which give you light. But is, how are we going to probe the rest of this stuff? I mean, we ended up deriving a lot more than just the energy levels. We derived stuff about L and m sub L. This is a way to probe it, okay? Because here's m sub L showing up directly. So in the 20s, two German physicists, Stern and Gerlach, set out to explore this. What they did, it's a famous result. I believe they got a Nobel Prize for this. They took a collection of, they made an atomic beam. What does it mean to have an atomic beam? That means you, in vacuum conditions, you somehow heat or accelerate. I think in most cases you just simply heat a gas, let it go through a little pinhole in a chamber into a vacuum, and you just send the atoms down in a vacuum, and you get to play with them, okay? So it's a beam of hydrogen. And then in a region, they had a magnetic field. This is a magnetic field like that. Let's call this the z-axis. And the beam goes right through the center. The magnetic field is only in the z direction. But the fact that it's curving, if you think about it a second, that means the strength is changing as I move in z. If I draw lines like this where they're denser, the magnetic field is higher. Where they're spread apart, the magnetic field is lower. Same with electric fields. So this is dB dz not equal to 0 right along there. And so then very simply, there's a force which is in general, the gradient, I'm sorry, left out the vector sign, or in one dimension, just the derivative of this. So it's just minus q ml h bar over 2m dB dz. This formula isn't so important except that it has m sub l in it, okay? So what were we going to probe? So basically we're saying, oh, if the atoms go through and they're in a state that has an m sub l, we'll get to see them moved by the magnetic field. It's going to interact with the dipole. It's this interaction of a magnetic field with a dipole. It's basically, two magnetic fields. It's the thing you do, if you have two magnets, and it's going to make them move. But so for instance, if I have the L equals 1 state, remember what our rules were. M sub L is 0, 1, 0, or minus 1. And just as a reminder, what am I talking about? I'm saying if I have L equals 1, that the angular momentum vector has a magnitude which is the square root of L times L plus 1 times h bar, which would be 1 times 2 h bar equals root 2 h bar. And that the projection of L on the z-axis was either h bar or 0 or minus h bar. Sorry, I got my drawing on top of my algebra. Let me just erase that. So the magnitude is root 2 h bar. And the physical picture is that L is doing this, this, or this. And M sub L, this is M sub L equals 1. This is M sub L equals 0. M sub L equals minus 1. By the way, this is sort of algebraically the class from here on, with the exception of when we do statistical mechanics, it's going to get simpler. Because I'm going to kind of just be telling you qualitative concepts. I'm just drawing simple little diagrams here, but you do need to understand this, because this is the reality of the system. And it's these kind of interesting little rules about what vectors are doing. Okay? So that's what it is. Now, if it was the L equals 0 state, remember that was also allowed. Little L equals 0. This is that capital L indeed is 0, and of course M sub L is 0. So we might think if the hydrogen goes through, it could be in the L equals 0 state, or it might be in the L equals 1 state or another state. If it was in the L equals 2 state, well here if the L equals 1 state, there's 1, 2, 3 possibilities. For M sub L equals 2, there's plus 2, 1, 0. That's 5 possibilities. So you would think that when these atoms went through, and if this is sort of a random collection, if they're all in the same L state, I might have thought I get one spot because L equals 0. Or I could have thought that if L equals 1, so the M sub L being plus 1 depends on the sign of this, and there's a minus sign and E is negative. But one of the ML equals 1 and minus 1 is going to be up here, one's going to be down here, and one's going to be undeflected because the L was aligned perpendicular to this magnetic field. When they did the experiment, what they found, always, and it turns out the hydrogen is usually in L equals 0. So that's what they were probing. They found 2 spots. Okay? So that doesn't fit into this picture at all. It doesn't fit into the L equals 0 picture. It doesn't fit into the L equals 1 picture, or any picture like that for the hydrogenic potential. And that's pretty disappointing, because quantum mechanics has just been developed, and hydrogen is the simplest atom, and there were only a couple of ways you can probe this stuff with the magnetic field. You can look at the resonance frequency, the Larmor frequency of precession, and then you can stick it in a non-uniform magnetic field. These guys did it. First answer, it's not L equal, the L picture isn't working. Okay? what they had discovered, the answer is that in fact L equals 0, but there's another piece of angular momentum. There's S, which is the spin. Okay? So sort of the physical microscopic picture is that the electron is this little sphere, and it's rotating, and it also has charge on it. Well, for the electron, it's minus E, uniformly. And it's spinning, and there's a simple angular momentum associated with the spin. And instead of calling it L, because I've already used L, we're going to call it S. But it's, it's more or less the same thing. But of course, keep in mind it's two different concepts. It's a very simple concept. Orbitally, like for planets, it's just the notion of the difference between the rotation of the Earth about the Sun and the rotation of the Earth about its own axis. Both of those have angular momentum associated with them. But there is a difference here. I solved Schrodinger's equation to get what I got for the atom. To get the fact that M sub L had certain values and that those should be interpreted as the angular momentum along the z direction. And that overall the length of the angular momentum vector was this funny beast, L times L plus 1 times h bar square root. For S, it's just handed to us as an experimental fact. You can sort of ground it in higher level theory, but at some level it's just imposed upon us as experimental fact. And also imposed upon us is the fact that the value of the spin is 1/2. Well, the way to think about it, we write lowercase s as a number which is a half. And this is analogous to L. That there's a vector spin. Well, let me not write the vector yet. There's a vector spin, the vector, whose magnitude is s times s plus 1. The same formula is for angular momentum. Okay? And so for the electron, it's a half times 3/2 h bar, which is root 3 over 2 h bar. Okay? And that there's m sub s, which is equal to minus 1/2 and plus 1/2 for an electron. Or more generally, for general spin s, n sub s is s minus s plus 1, add 1, add 1, add 1, and come up to s. Okay? And then there's a difference. If s is integer, this is going to go minus s, dot, 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 0, dot, 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 out to s. But if s is a half integer, it's going to be different. So for instance, minus 3/2, minus 1/2, 1/2, 3/2. It skips 0. Not a big deal, but that's just what it does. Okay? That's how it would work. So the formulas are the same as for angular momentum, but it's just there. There's no wave function associated with it. Right? There was a wave function associated with L. When I derived about L, and I found m sub L and all that, right? There was that associated Legendre polynomial. You can look it up. You have homework where you ask you to work some stuff out about them, right? And it's a cosine and blah, 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 blah. And the phi part, which is L sub z, was e to the I. No, there's no wave function associated with the spin. In fact, you want to get it weirder? As far as we know, there is no size to an electron. Okay? Particle physics experiments where you collide particles at each other. If the electron had a size, the electron has a force field from electricity and magnetism, just a Coulomb force field. When you collide two electrons, they will scatter off of each other, and they act as if they're just acting under the influence of each other's mutual electric field. If the charge of the electron and the mass of the electron were contained in some little hardened nugget. Okay? And I tried to get those two hard nuggets to hit. I need a lot of energy because the force between the two hard nuggets is 1 over 4 pi epsilon naught E squared over R squared, right? And it's a repulsive force. I leave off the sign, but you know it's this repulsive force if the two electrons have the same charge. So as I get closer and closer and closer, the force is infinite. Or the potential, where I leave off 1 power of R, is infinite. It goes to infinity as R gets smaller. So there's a bit of an intangible question, how small is it? But the fact is that the energy scales we've probed so far, we don't see a little hard nugget where suddenly the collision looks different than it did as if it just scattered due to this force field. Okay? That's a whole branch of physics, particle physics, where we collide particles. The same doesn't hold true at all for nuclei. If I smash a proton into a proton, if I do it at low enough energies, they never hit each other because I don't overcome this force, the so-called Coulomb barrier. But once I overcome it, then you break them apart and you get out all sorts of other stuff. And by looking at the angle at which the particles came out, you can tell if they just had this sort of repulsive force interaction or they actually smacked. There were two little nuggets that smacked each other. Okay? Well, the fact is that for electrons, to the energy scales we've been able to probe, which is a very high energy scale, many, many times the electron rest mass, mc squared, there's no size to it. As far as we know, it's point-like. How can a point-like particle have a spin associated with it? Well, okay, there's several mysteries. How can it have a charge associated with it? How can it have a mass associated with it? And okay, if I forget about those, the mystery today is how can it have a spin associated with it? Because what's the thing that's spinning around if there's no size to it? Okay, so those are good questions for which I have no answer. But the fact is, it has a spin associated with this point-like particle. One other thing, if this were a classical particle and it's spinning like the Earth, or like, someone on ice, what does someone on ice eventually do? They get dizzy and barf, or they fall. They slow down, right? This spin that's associated with an electron is just a constant. It never goes away. There's no S. If the particle has a spin of a half, that's it. It has a spin of a half. So it is kind of odd. Then you might say, well, okay, it's some weird quantum mechanical thing, but it's not really a spin. Well, no, because the way we found it is we did an experiment whose description was classical. I derived this force. That's a classical result. Except that I put in h bar as the z component of the angular momentum. And that's what it did. So there is a real physical spin, but whose physical interpretation is a bit odd because we don't really know what we mean by the physical nature of the electron down. Maybe it's just simply that it is a little tiny sphere, and it's so tiny that we haven't been able to get to energies big enough to probe it yet. In some sense, maybe that's true. Probably that's true, but we just don't know. Anyway, okay. So enough philosophizing. Electrons have spin. In fact, all subatomic particles have spin. And sorry. And how do we know it's a half? We know it's a half from just this sort of measurement. Okay, and also it only makes, because if I did calibrate this, and I know that, then I'm measuring m sub L when I know h bar. I know the force and distance, and I do kinematics, sort of like your cannonball in first semester, right? So I calculate it when it turns out it's a half, yeah.
So if it's a half, then what is all this minus s plus 1?
I start off with minus a half. I add plus 1, I get to 1 half.
Well, yeah, but can't you just say that it's always, like, if s is always a half, then or is it always a half? That's what I don't understand.
Wait. Good point. This was m sub s. What is m sub s? How much of the spin is along the z-axis? Okay? Remember, again, this is a weird thing. When you have a quantum mechanical thing that has angular momentum, I have two thoughts. Let me finish the first thought. When you have a quantum mechanical thing that has angular momentum, a vector s, it doesn't, it just, quantum mechanically, uncertainty principle wise, it simply isn't a vector that has any old orientation in space. Somehow I measure the system, I interact with the system, I probe the system, that defines a z-axis. And this thing will line up such that its projection along the z-axis, and here I'm drawing a spin 1/2 particle, is either going to be, so the value of S is, this formula is 3,2 h bar. It's either going to be aligned up on the z-axis such that the z component of S is 1/2 h bar, which is to say the m sub s equals 1/2 state, or it's down here where where minus 1/2 h bar is equal to S sub z, which is to say the m sub s equals minus 1/2 state. And it's sort of indeterminate as to what direction it is along the x and y axes. And in fact, it's fundamentally indeterminate in an uncertainty principle way. It simply can't have a well-defined x and y component. You just know how much rotated it is compared to the z-axis. Yeah?
Does it always happen that in these quantum mechanical systems, we have a certain symmetry about the xy plane?
Yes, but that's just to say, okay, remember, of course, z was arbitrary. There is some axis, we'll always call it z. If I have a projection along z, that just means it's uniform in x and y, but uniformly unknown.
Yeah.
I mean, the picture we like, the book has drawings of this, is that it's just that we know that the vector has a certain length, and that we know it's got some number in x and y that we don't know. We know that we don't know it. It's a known unknown, a Rumsfeldian known unknown. And the z is a Rumsfeldian known. Okay? In fact, look, I mean, this picture should be taken literally, right? If if the magnitude is √3/2 h bar, and the z component is 1/2 h bar, what's that angle? It's 60. Right? That's 60 degrees, that's 60 degrees. I didn't draw it that well, because that means that's actually 60 degrees, right? That's the picture. It's just that. I said I had two thoughts. The second thought was that, and I'm going to kind of reiterate again, that we derived this for the angular momentum of a particle in a circular orbit with a hydrogenic potential, with a Coulomb potential. So the hydrogen atom. But the result is more generally, the result is more general. Even if the potential isn't exactly a Coulomb potential, etc. Even if it's spin, for which there's no potential per se, any quantum mechanical or angular momentum has those properties. And there's sort of more abstract ways of formulating quantum mechanics where this will just pop out as a result. And you're not starting with that associative Legendre polynomial and those god-awful differential equations. These are just sort of the facts, if you will. Okay? And so the m sub s was just, had these properties. Let me mention real quick, if you count the values of m sub s, the number of states of m sub s is equal to 2s plus 1, right? Because there's these. This is the thing I think I told you Euler did, right? It's just the ends, etc. Same with L. Number of states of m sub L is equal to 2L plus 1. And we're going to need to know that later, right? And, I'm not doing anything mysterious here, right? Suppose I had m sub s. Suppose I had s equals 2 or L equals 2. There's 1, 2, 3, 4, 5. It's obviously, that's just 2 times 2 plus 1. Yeah?
Does that hold true though if s is a half meter because 0 is
Yeah, does it?
it's not.
So if s is 1/2, then I have minus 1/2. I have 2. 2 times 1/2 is 1 plus 1. It works. If I have 3/2, clearly it's 4 states. So it was 2 times 3 halves plus 1 equals 4. Yep, it does work. Kind of neat, right? So this always works. Good questions. All right. This is easier than and more fun than solving hairy differential equations, is it not? Okay. I was going to list some particles and what their spins are. The photon, well, okay, let me start. The fundamental, the standard sort of particles that are tangible that we know about are a half. Quarks, which are the things that make up neutrons and protons, are also a half. A neutrino, which I've mentioned, is a half. A photon is 1. Yeah. Kind of have a faulty connection between my brain and the rest of me sometimes. Yeah. Why does a photon have a spin? You learned about plane waves and electricity and magnetism, right? And you learned that, so it's an oscillating E and B field. And the one way you can look at it, the fields do that. But the other way you look at it, the B and the E are out of phase such that a vector rotates, so it's circularly polarized. The quantum mechanical view of light is it is that wave, but the fundamental states, the photons, are always a bit of circularly polarized light. Okay? And so they're L equals 1. They're a little bit of a special case, but to the extent you consider them to have a spin, they have a spin of 1. And they do have a spin. They're not spinless. And so in some sense, there's not a single photon that is the uncircularly polarized version. It's always going to be the circularly polarized version. And then there's a graviton, which we are certain is there. Well, we're sort of certain it's there, but we've never measured. It may never measure. It's a spin of 2. And there's other things. There's pions, which are 2 quarks. And you might, if a quark is half, sort of it can cancel. A half, I add another one, I get a minus half. I add a third one, I get a half again. And it's sort of vague statement, but in fact it's true. And that's why with quarks being a half, neutrons and protons were 1. Pions are 2 quarks, and they'll be 0. Although you can make 3 quark objects that have spin 1, and you can make 2 quark objects that have spin 1 as well. But, 3 quark objects that have spin of 3 halves. Okay. And finally, one last comment. Because there's no wave function for this spin, we need a new notation to talk about it if we're going to write it down. So the notation. And let me just focus on electrons. The m sub s equals 1 state, 1/2 state. We talk about it as spin up. So that, I call it spin up. It means I defined some z-axis, and I meant it was, the positive z direction. The notation for it is this. Or sometimes people will do that. That's a ket from the word bracket. So the analogy of psi is that. The analogy of psi star is that. Spin up. The analogy of psi star is to just draw the ket backwards. In fact, so it's called a bra. And so the two of them together are a bracket. So that's a bra, this is a bra, and this is a ket. And so the analogy of psi star psi is up, or down, and that's 1. Okay? It seems like I'm just playing games and writing simple things. But I'm not, because things get a little bit complicated here, and I need a very simple way to describe them. It's going to get complicated later. And I don't actually do an integral. If I write that down times that, it's somehow like I integrated, and the answer is 1. Okay? You think I'm kidding? People call them bras and cats. Okay. What happens if okay, so now, the fact is that if I have the electron whizzing around in an atom, I have the electron, and it's, whizzing around in the atom, so there's L, and it also has S. What do I do with L and S? As you can maybe anticipate, it's not totally simple, okay? I'm going to have J equals L plus S as the total angular momentum. The total angular momentum vector, whereas this is called the spin, and this is the orbit. Or this is the orbital angular momentum, and that's the spin angular momentum. Okay? Angular momentum, spin, angular momentum. I mean, if I write it down like that, okay, I just said I added 2 vectors. Fine, so what? I mean, here was L, and here was S. And I can think of, that's fine, there's nothing wrong with that, but let me instead translate this vector out to here, and then that would be my, my picture of J, right? Adding 2 vectors. Okay, but it's not that simple. I've said that if I have the angular momentum vectors, L or S, that I pick some z-axis and then the value m sub s, m sub l, in other words, the angle that the angular momentum vector makes with that axis, that z-axis that I just sort of picked out of the air, is the thing that's determined, and the other 2 are not. This comes back to this notion which we have in quantum mechanics, is that systems kind of don't really take definition until, well, one school of thought is that you talk about measuring them. When I measure them, I put them into a state. I put them into an eigenstate, okay? I'll then, for the first time, define the z-axis, which has a definite value while the x and y do not for the angular momentum. I don't really like that measurement language myself. I think if it interacts with something, that's the thing that does it. Well, these 2 things interact with each other because they're both creating little magnetic fields. And the 2 little magnetic fields, they interact with each other. In fact, there's something called the spin-orbit coupling. And there's an energy. I won't write the full formula. There's a constant, which is in the book. And it's proportional to S dot L. Okay? It comes from, if you will, you can think, U, I said, was, this is a potential energy, was mu dot B in general. Either of these dipoles is creating a magnetic field, which you can think of as the other one, interacting with. And you can think of it either way, it's symmetric. The point is, it amounts to an energy which couples the mu of the one with the B of the other, and they're both, it's S dot L. So the 2 interact and there's an energy, and I wanted you just to file that away, that there's this spin-orbit coupling. It's about 10 to the minus 5 electron volts, compared to 13.6 eV. So it's a very fine detail. So sometimes this is called the fine structure. It does mean that if you have an atom that has a value of L, different values of S change the actual energy of the orbit. And where it shows up is if you look at atomic spectra, you basically see the lines that you told about, like the Lyman alpha lines in hydrogen, or the Lyman beta, or the Paschen lines, all those lines. Okay? If you look at them in detail, there's actually more than one line, and it's because of different orientations of L and S. Okay? And so this really does show up and it's measurable. Yeah. No, you're just holding that up. Okay. Fine. Now, and we're out of time. Let me just say one concept while it's on my mind without writing, I think, anything else down then. I'll draw one picture. So the basic idea then is that if I have L and S interact, they create the mutual field for each other to define the axis for which then there can be a specified Z, a specified component. So basically, if L is like that, S, let's talk about S being 1/2 here, an electron, okay? M sub S shouldn't be defined relative to some arbitrary Z in space, it should be defined relative to Z. So in other words, I really only have two choices, with that being the 60-degree angle we talked about. S should either be that way, because that's a projection of 1/2 h bar onto L, or it should be that way. This is essentially spin up. Well, this is sort of S and L aligned. Yeah. And this is S and L anti-aligned. And so in this case, I'm going to have J of that size, and in this case, I'm going to have J of that size. Okay? Fairly simple concept, and that's what happens. So let me just leave it at that for today, and then we'll think about the implications of that on Monday. Homework due on Monday.